Welcome to Lesson 6F, Vorticity, Flat Plate Boundary Layer. In this lesson, we'll apply the concepts of vorticity production at a wall to a two-dimensional flat plate boundary layer. In the previous lesson, we discussed 2D airfoils. As we'll see, the flat plate boundary layer is more of a mystery since there is no pressure gradient, yet there is vorticity. Where then is this vorticity produced? Here's our setup. We have a thin flat plate, and we'll use coordinates x1 and x2. This plate is infinite into the page, and the flow upstream is uniform at u infinity. We'll greatly exaggerate the thickness of the boundary layer, delta, which is a function of x1, and the velocity profiles look something like this. At the edge, the speed is u infinity, since that's the speed above the boundary layer, and delta, or the boundary layer thickness, keeps growing downstream. If we look more closely at one of these boundary layers, where we'll plot u1, it looks something like this, and as we'll see in a later lesson, this is the Blasius boundary layer. We'll actually show how to solve for this in a later lesson. Right at the wall, it turns out that the profile is linear. In other words, there's no curvature right at the wall. We also make the approximation that del P del x1 is 0. In other words, there's 0 pressure gradient in this flat plate boundary layer. Now let's recall equation 4 from a previous lesson, which was del omega 3 del x2 equal minus 1 over mu del P del x1 at the wall. Well, here, since del P del x1 is 0, del omega 3 del x2 equals 0 at the wall. In other words, the 0 pressure gradient at the wall results in a 0 vorticity slope at the wall, or what we usually say is 0 vorticity gradient at the wall. We also know that omega 3 for this two-dimensional problem is del u2 del x1 minus del u1 del x2, but since u2 is 0 everywhere along the wall, this term is also 0, which leads to then omega 3 is minus del u1 del x2. Again, this applies at the wall. But as we said, right at the wall, the velocity profile is linear, and a linear velocity profile near the wall means that del u1 del x2 is constant at the wall. And this equation then tells us that omega 3, the third component of vorticity, is constant near the wall. This statement agrees with what we showed here. Since there's 0 vorticity gradient at the wall, or near the wall, omega 3 must be constant near the wall. So we basically said the same thing twice in two different ways, using two different analyses. Going back to this equation, for our flat plate boundary layer, there's no pressure gradient along the wall. And there's no vorticity gradient at the wall either. And from our previous lessons, we know that therefore there is no vorticity production at the wall. I'll also plot the vorticity component, omega 3, as a function of distance from the wall, x2. It turns out that the vorticity profile looks something like that, where we know that vorticity is clockwise or negative on the top portion of the boundary layer. In other words, omega 3 is less than 0, as plotted. And we also know, as we've shown above, that the slope or gradient of omega 3 with respect to x2 is 0. In other words, del omega 3 del x2 equals 0. And that's the way I've sketched it here with 0 slope. Again, 0 slope of vorticity at the wall means that no vorticity is being produced at the wall of this flat plate boundary layer. I'll make a summary statement from all this work. No vorticity is produced at the wall of a flat plate boundary layer.
But sir, we know that there's vorticity in the flow, so where does it come from?
That's a good question, Ned. Where then is vorticity produced? We don't seem to have a mechanism of producing vorticity, yet we know there's vorticity in the flow. Looking at the whole flow field, we have uniform flow upstream of the flat plate with constant speed u infinity, and we'll let this plate go on forever, but it starts at x1 equals 0. The boundary layer grows on both sides of the plate, and at some downstream distance, the velocity profile looks something like that, with the mirror image on the bottom side. Because of this profile shape, we know that fluid particles will rotate since the top of the particle is moving faster than the bottom. A fluid particle above the plate thus has a negative omega-3. Again, on the bottom boundary layer, everything is mirror imaged, and the vorticity component is positive. There's no vorticity here, but there is vorticity here in the boundary layer. Yet we said that no vorticity is produced at the wall. So again, we ask, where then is this vorticity produced?
Is there some kind of a bound vortex like you showed us for the case of the airfoil?
No, there's no bound vortex or starting vortex here, because there's no lift. In fact, all the circulation at the top cancels that at the bottom. There's no net circulation around this flat plate. The answer to this question is that vorticity is produced at the leading edge of the plate. All of the vorticity that we find in this boundary layer is produced right here at the leading edge. We typically analyze the flat plate as an infinitesimally thin plate, but if we zoom in on this region with a magnifying glass, what would we see? If we zoom in far enough, the leading edge may be some kind of a rounded shape, as shown here, and the plate has to have some thickness. Just as we discussed with the 2D airfoil, we have a negative pressure gradient in this region. In other words, we have an accelerating flow from the stagnation point to U infinity, which, as we recall from the previous lessons, a negative del P del x1 leads to a production of negative vorticity. Similarly, in this region, there's a production of positive vorticity. So we see that all of the vorticity, both negative and positive vorticity that exists in the boundary layer, is produced at the leading edge. There's zero production everywhere else except at the leading edge. By the way, you can make the similar argument for a pointed leading edge, where there will still be regions of flow acceleration at the top and the bottom, just as we had here, where vorticity is produced. What happens to this vorticity produced at the leading edge? Let's look at just the top portion where the boundary layer is growing as shown, and all the vorticity is produced at the leading edge and nowhere else. That vorticity is convected, or I prefer the term advected, downstream, and it's also diffused away from the wall. The vorticity gets redistributed both by advection and by diffusion. Note that the flow inside the boundary layer is rotational, and the flow outside the boundary layer remains irrotational. We'll spend many lessons on boundary layers, but for now the boundary layer approximation is that advection is much faster than diffusion, and we're talking about viscous diffusion, of course, since this is a laminar boundary layer. This approximation implies that the vorticity is confined to a thin region near the wall, which we call a boundary layer. Perhaps you can visualize the advection and the diffusion by plotting vorticity profiles. If this is our flat plate, and this is our exaggerated boundary layer thickness, vorticity profiles, namely omega-3 as a function of x2, will look something like this, very close to the leading edge, but farther downstream, the vorticity magnitude decreases, but it diffuses outward as it advects downstream. Even farther downstream, the magnitude decreases more and it spreads out more. Since all the vorticity is produced here, vorticity can only be redistributed downstream. No new vorticity is being produced in this flow. Let's do a quick example problem, namely, simplify the vorticity equation at the wall of a 2D flat plate boundary layer. To solve this, we go back to our vorticity equation from a previous lesson, but recall that for 2D flow, the vortex stretching and tilting term is 0. So the vorticity equation reduces to d omega k dt equal nu del squared omega k del xj del xj. But again, since the flow is 2D in the x1, x2 plane, omega-3 is the only non-zero component of vorticity. So for k equal 3 in our equation, we write del omega-3 del t plus u1 del omega-3 del x1 plus u2 del omega-3 del x2 plus u3 del omega-3 del x3 equal nu times the quantity del squared omega-3 del x1. Note that some people will write del x1 squared, but I like to keep it like this in tensor notation, plus del squared omega 3 del x2 plus the j equal 3 term as we sum over j. But many of these terms go away. We're talking about steady flow, 2D flow, and this one, by the boundary layer approximation, the first term is very small since del x1 is much smaller than del x2, and we're doing this twice. Furthermore, we're talking about at the wall, where the no slip condition tells us that u1 and u2 are 0. Therefore, these two terms also go away. Finally, this term goes away because there are no changes in the x3 direction. So everything has dropped out except this term, and so our final result is del squared omega 3 del x2 equals 0. That's our final vorticity equation at the wall. I comment that this second derivative implies that the vorticity has 0 curvature near the wall. So in our vorticity profile, where we plot omega 3 as a function of x2, and it looks something like this, we not only know that del omega 3 del x2 equals 0 at the wall, in other words, there's no slope, but we also know that the curvature at the wall is also 0. Recall from your math class that 0 curvature means constant slope, but it turns out that that constant slope is actually 0 slope, which is the whole reason why vorticity is not produced at the wall. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.